Hello. Hi. So this is going to be a practice run for my talk at ELS next Tuesday. I haven't practiced at all before, so this is going to be my first time doing this. I have no idea how I'm going to do in regards to time. Ideally, I should be taking around 20 to 25 minutes of talking, and the rest of the time should be either wasted on setup or used for questions from the audience. So hopefully if I pace myself correctly, which I probably won't because usually when I do presentations I talk way too quickly. But if I do, then this will take around 20 minutes. So yeah. TTS won't be on, so don't bother writing to me until we're done with the presentation. But if you want to chat and discuss things or write them down as you notice them, of course you're more than welcome to. Mostly looking to, one, try this for myself for the first time so I have to practice a bit, and two, to potentially get some feedback, some preliminary feedback to see if there's anything that I can improve about it so that it goes smoothly when the real deal arrives. Now, it would be great if my birds were less rowdy right now, but I don't think they're going to comply with me because they have their own ideas of whatever they should be doing, which usually do not coincide with my own. But them's the breaks. There will not be a bird cam. So, the main differences, I suppose, to the actual talk that is going to be happening next week is obviously, one, there's birds in the background, and two, you don't actually see me, so you don't see me gesturing, and it feels a bit detached, which is a bit weird, but hopefully most of the talk is still gonna, you know, feel the way it should. Actually, hold on for a sec. Stuff. If that actually works. Got one of these station device thingies. It does. Amazing. I don't want to turn on my camera. No. Because I would have to, like, position it really weirdly to get myself into frame. And I don't want to waste time on that. Anyway. Let's get going, huh? Okay. Alright. Sure. Okay. Hi. Welcome to my presentation on basically a technique I've been investigating on how to make graphics programming a bit more modular and a bit more bearable in using some techniques that are generally applicable and some techniques that are more specific to Common Lisp, I should say. But first off, let's just, you know, have a bit of an introduction about modern graphics and all of that stuff. So, way back in the olden days, you had a different way of drawing things, which is basically you had an API that you would call, and that would talk to your graphics processing unit, and that graphics processing unit would then draw things to a screen. They would say, okay, basically say, okay, I'm starting to draw vertices now. And then he would say, I'm drawing this vertex, and then this vertex, and then this vertex. And he would basically, for each, every vertex and every kind of property you wanted to specify for the GPU, will perform a call to the graphics API. And that works fine for 1990s technology. But the problem is, once you start to up the complexity of what you're going to draw, this quickly becomes infeasible. And the reason is that every time you have to do a graphics API call, you need to synchronize what you're doing with the GPU. And this is very costly, it turns out. because you're taking up space on the graphics bus. You need to load up data and so forth and so forth. So this is very costly, and so things changed around. And now with modern graphics, what you want to do is to upload as much ahead of time as possible. So what you're going to do is, instead of, specifying each vertex every time you draw it, you take all the vertices, stuff them into a data buffer, and then you upload that data buffer. And then it's there on the graphics card. And then you just tell the graphics driver, okay, now draw me all that data. This is done for both data that is specifically vertex data and like textures, so images and stuff. And it's also done for code, because while previously in the olden days, you used to have very specific kind of included ways of drawing things. So the way things are rendered was already done for you in the graphics driver. Nowadays, the way you want to do things is so complex and so domain specific that that's really not feasible anymore. So you have to handle the drawing logic yourself, and in order to facilitate that, the driver needs to allow you to write code that ultimately runs on the GPU. So in the case of OpenGL, this language for GPU-side code is called GLSL. It is a C-like language, so it looks kind of like C, but it isn't really. It has some major differences. It is specifically made for graphics, so there's a lot of things that are specific about GPU programming and specific about graphics in particular. And the way you actually, interact with these programs is you put them into a string, so a string of code, and then you pass that string to the driver and say, okay, compile me that thing, and it does its magic of somehow compiling that into whatever kind of format the GPU expects. So this is done because obviously, or well, not necessarily obviously, but traditionally graphics vendors are very secretive about how their graphics cards work. So they want to retain control over how things are executed on their GPUs, which means the details and specifics about how things work is not known to you. Thankfully, usually that's not a problem. So here's an example of some GLSL code. This would be for a fragment shader, but we'll get to what that means later. So what you have is some sort of global definitions that either define variables that you can interact with from the CPU, or variables that interact between different kinds of stages during the rendering. And then you have one main function that is called for this program, and that does all the actual logic of rendering. So in this case, we're just computing some kind of color to output. So this is an image of the OpenGL render pipeline. So these are the steps that your GPU or your driver performs every time something is drawn. So every time you tell the driver to draw things, all of these steps are executed on the GPU, and a lot of them are highly parallel. So GPU programming is very specifically about parallel programming and making things run really, really fast. So in particular, you want to look at the orange shaded stages here, because those are the ones that you can actually influence. Those are the ones you can write programs for. The rest of the stages are specific to the driver, and they cannot be accessed, so those are fixed. In the olden days, what used to be the case is that the entire pipeline was fixed, and you had a huge amount of variables that you could set and control from the CPU in order to influence how things are drawn in specific ways. But naturally, that is a very limited way of doing things. So this is now the way things look today using OpenGL 4. Well, 3+, I could say. So this is all nice, but there's a problem with it. because oftentimes, especially when your programs grow or when you want to make things easy to digest for users, you want to be able to modularize things. You want to be able to take them apart into select units, and you want to be able to combine those units to form your entire thing. You don't want to have to write a huge block of code every time. Now, this is not possible with the way the render pipeline works. So the way things work in OpenGL is that each of these stages, each of the orange stages, can hold one program at a time. So when you draw it, you can only specify one particular program to be executed in that stage. This is a bit of a problem because when you have concrete units that do something particular but relatively small, and you would like to combine that with other things, then that's no longer possible. You need to have some kind of logic in place to combine these things together down to a single program so that OpenGL can accept it. For a simple example, you could say in the fragment stage decides what color each pixel is going to have. For instance, you might have a, let's say, for a primitive example, let's say you have a fragment shader that encapsulates the logic to apply a texture. So you have polygons, and then you have a fragment shader that draws a texture onto this polygon. So it knows the logic of that. And then you, for instance, have a fragment shader that, I don't know, maybe applies some kind of distortion or some kind of other effect that would also influence the fragments directly. So you want to have both of those. You want to have a texture unit, and you want to have those textures distorted somehow. And now you have to have some kind of way of combining these two together. So there's multiple kinds of ways of doing this. In prior work, what I've seen is that we'll get to fragment shader examples later. So if you can't really picture it in your head, we'll get to it, don't worry. So what I've seen in other literature done is primarily either controlling how you do things entirely. So you have an entirely new language that is then translated to GLSL. If you do that, then obviously you have control over everything and you can do whatever you want. So that's one approach I've seen. The other approach, another approach I've seen is really crazy, which is that you write lots of pieces of code that are commented out through if-defs. So the GLSL code allows you to write preprocessor macros in there, and then you write like one huge chunk of code, and sections of it are commented out through if-defs. So when you want to combine things, you simply activate only the parts you want. Obviously this, you know, it works, but I would not want to dare touch anything that monstrous myself. And the final one is what I've seen is like sort of building large libraries where you encapsulate all the functionality in functions, and then you have a way to include these functions in your file and then call them that way. So that's a bit nicer, but also not quite workable, because then you run into the problem of, if you go back here, you have these global variable definitions, and because the function cannot know what they're called, it needs to now take all of these parameters as function arguments. And so things can get quite messy there, where you have to pass a plethora of different kinds of arguments now. So there's different kinds of solutions to this already, but we have a sort of a new one that I haven't seen anywhere else before. I'm not sure if I'm the first one, but maybe I am. Who knows? So our solution is to parse GLSL into an AST. So we have a program that can take GLSL code in string format, and it can turn that into an AST. So it's a full parser for GLSL. And then what we can do is we can do code walking and semantic analysis on this AST. And to do that, With that, we can then merge these programs together in a way that makes sense. So we can take programs that are written just like this. They can assume that they're the only ones running, and we can analyze them. We can find the main function. We can find all the global declarations and references to the variables. And we can do that for many different kinds of code snippets. And then we can figure out how to rewrite the code in order to merge those together so that they still work as one thing. So that's sort of the first step of this. And then the final step is for us to attach these kinds of shaders to objects in our system, which allows us then to simply use inheritance to combine effects together in a much more natural and intuitive way. Right, so the first step is called GLSL Toolkit. As I said, it implements a full GLSL 4.1 parser and a code walker for semantic analysis. And unless you want to do more fancy stuff, you can do that. You can use it to check for correctness, or perhaps even implement things like optimization passes or rewriting or something like that. Or maybe linting, I don't know. But if you just want to merge things together, you have just one single function that you can call on two code snippets, and it'll do all the logic for you and spit out a new source code that you can use in place of the two separate parts. So here's an example. We take our previous fragment shader code and run it through parse, and it spits out an S expression form of the entire program that we can then easily traverse and look at. So it's a bit longer than this. Obviously, I had to truncate it, but I'm guessing you get the gist of it. But, you know, this entire shader business parsing and stuff isn't really specific to Lisp. Anyone can do that. So where is what makes this Lisp specific? Well, we're getting to that. Before we do, though, I'm assuming that some of you are in the audience don't really know CLOS and MOP very well. So I thought I would give a bit of an explanation of what how CLOS works and what makes it different. So CLOS is the common Lisp object system, and MOP is the meta object protocol. And specific to our case, important is to note that CLOS allows you to inherit from multiple classes at the same time. So object systems like Java or C# do not allow you to inherit from multiple classes at the same time, because that can cause problems in their systems. But in CLOS, this is actually encouraged and a very often used technique to define like small pieces of code as a separate class. So, well, not code, small pieces of behavior as a separate class, and then combine all these separate pieces of behavior into one big class that defines everything you want. These small pieces are called mixins, and they're very, very handy. But another important thing to mention is that through the extension of the MOP, you can influence not only the behavior of objects through the classes, you can also influence the behavior of classes themselves. So there's a sort of a turtle scheme going on here, where it's classes all the way down. So a class, an object has a class, and the class has a metaclass, and the metaclass can have a metaclass, and so forth, until infinity. Now, that might be a bit scary to imagine right now, but what's important is simply to imagine that if you have a class, you can attach more information to it. So you can not only store information in instances, you can also store information in the class itself that isn't the fields and slots that you have otherwise. And this can be done with the MOP. So what we want to do, of course, is we want to build one of those metaclasses that now allows you to attach shader sources, so that you can define a class, and then you can say, okay, this class has this kind of shader code attached to it, so that it knows how to draw instances of this class. And when we inherit different classes, we merge these shader sources together using the GLSL toolkit. And the fantastic thing about all this is that thanks to CLOS's strict class-precedence protocol, we know exactly in which way these combinations are going to happen. So it is well defined, and you know what to expect when you specify different kinds of mix-ins for different effects and shaders. So here's an example. This is a teapot. It's not very exciting. We simply define a shader subject here called teapot, and we inherit from slide subject, which does a bit of positioning on the slide here, and it also allows you to define vertex data attached to it. So we have teapot in vertex data somewhere in memory, and we have a handler here that allows it to rotate. So this is basically a simple definition. We'll get to more complicated examples later. But for now, let's take a look at attaching shader codes to this teapot. Do like this. So we have our shader subject definition again. And now through define class shader, we can attach different kinds of shaders to this class. So here we have the same fragment shader from before again, and now we see what it actually does. It does some actually quite fancy effects for the little amount of code that it is. As you can see, it does two things in particular. One is it adds these red and white stripes, or red stripes over the teapot. This is done through this line here, which is simply using the X and Y coordinates to do some arithmetic shuffling, and then uses that to calculate the red colors. And then you have this other effect, which is sort of a fake kind of rendering by using the depth coordinate. So how far in the vertex is in the screen, how deep it is, determines how light it is. And that way we get a sort of a very cheap, but still quite nice looking shading going on. Okay, good. Okay, yeah, thanks for the reminder. That's good. Right, so now that we have a way of attaching shader codes to the class, we can take a look at how we can combine these through mix-ins. So in this example, we have our teapot again, which is still a slide subject, but now we can add, for instance, a textured entity to it. And immediately you see that it now changed to being textured. The teapot now has a very odd looking brick pattern across it. Below here you can see what's happening in the fragment shader. So for instance, if I go back to this, you can see the fragment shader is a very simple combination that basically all it does is emits a white color. So it has a main function, and that calls another stub main function that simply emits white as the output color. When we add this textured entity in, what happens is you can see below there's now a second sort of definition mixed in, which takes in a texture coordinate and a texture image, and then uses its own sort of separate main function to add this texture color to the main color. And then both of these main functions are called in sequence. So here you already see this kind of combination effect happening, where you can easily merge behaviors together. But that's not very interesting. But we can add more stuff to it. For instance, we can also make it bluish by adding a colored entity alongside it. And now the shader is more complex still. We have another effect added to it, which is this color multiplication. And the color is actually passed along from the CPU using this uniform parameter. Right, so for instance, we can also change this to be red, I suppose. Maybe. Or not. Wait, why doesn't that work? Probably overriding it somewhere else. Okay, I'll have to check that somewhere else. Some other time. before I do this presentation, I mean. Yeah. Alright, it's being overridden again, which is why it's blue. Yeah, it is a bit dark. I'll fix that. Hold on for a sec. I'll fix that right now. Where is it? Is it? I'll make it a bit lighter. Yeah, that's a bit better, I guess. I don't know. Hold on though. Yeah. Okay. Just one. Ah, fuck. Nothing's moved around. That's. I'll fix that later. Okay. Anyway, so using these kinds of mix-ins, we can encapsulate individual functionality. We're doing very specific small tasks, and then simply combine them according to what we need. So that's great and all, super probably, but obviously, as always, there's got to be a catch. And the catch is of several natures. So some shaders are not automatically mergeable, so some things are incompatible with each other. So if we go back here, for instance, if you have a global declaration, for instance, of vertex data, that does not agree on its types, then this is not resolvable. The system does not know how to do this, and I'm not sure if in general you even can, because there might be different intentions in mind and different ideas about how things should work, which makes it not possible to always do this. The current strategy we employ in order to actually perform the merging is extremely primitive, so we don't actually do a lot of work. Pretty much the most we do is we look at the global declarations, and there's a new one, we remember that name, and then whenever we see that declaration again, but with a different name, we sort of give that name an alias to the previous one, and then just rewrite it whenever we see it next. And then we have some special handling for the main functions so that we can call them all in sequence, and that's it. So it really doesn't do much right now. It is sufficient for a large number of examples, but especially when you get to more complicated shaders that do more things and assume more things about things, you can run into the issue that the system will not be able to figure out what to do on its own, and then you have to intervene and change things on your own and fix them manually. Ideally, what initially the idea was of this system was that you should be able to just, you know, drag any kind of shader off the internet. There's a great website called Shader Toy. There's like tons of different effects and stuff on there. Really cool stuff. And you should be able to just drag and drop one of those onto your hard drive and then, you know, immediately use it. But that's that's a bit of a pipe dream because of how much stuff you can do and how little information the system has about what the user really means, you know. You run into this kind of issue all the time. But for a large class of things, this actually works fine. But we could definitely be much smarter about things and definitely like also offer the user aid in how to do things. Now, another important thing is that how the effects are combined may not be intuitive, and some shaders might also need to be adapted. So for instance, if we go back here and we take a look at code, you can see that, hold on, let me make the cursor because I don't have a laser pointer on this. You can see that in these main functions, what we do is we always multiply the output color with a new one instead of assigning it. Because if we simply assigned, what would happen instead is that whatever kind of color a different kind of previous function might have emitted is now overridden and entirely lost. So that's usually not what we want, but this multiplication might also not be the kind of combination behavior we might want. So ideally the system would be able to automatically recognize when things are combined or overwritten and then offer advice or easy methods to change that behavior in a way you want. So for instance, if you don't want multiplication, you might want to have some kind of non-linear behavior or something like that. You should be able to add that in easily, but currently you can't. The system isn't smart enough for that. And in some cases it might not be feasible to even determine it. I'm not sure about that, but you know. Hold on. Right. So aside from those things, you know, that are purely deficiencies of my own system that can be to some point corrected, there's other things we can do with this, because we now have a way of analyzing GLSL code. We can do things like verify correctness before you send it to the driver, which is really nice, because then you don't need to wait for the driver to tell you that your code is wrong, because you can do it ahead of time. And possibly you can even offer better advice than the driver does. Some of the drivers are really bad. They don't really tell you what the hell is going on or what's wrong. So, or they might even take wrong code and still compile it after all, so that's cool. And then you get like really weird effects and you don't know what the hell is happening. So there's lots of areas here where you can do interesting stuff. So verifying correctness and offering advice would be definitely one area that I would love to have more work done in. And then otherwise you could do things like trying to do optimization passes by analyzing code. I don't really know what current drivers do, if they do any optimization at all, or if they just, you know, take the user's word for it and then just emit the code verbatim. You could obviously do all those kinds of things like unrolling and whatever that you can do in usual optimization things for code system compilers, you know. Yeah, automatic correction for problems might be another one, so that you can catch suspicious behavior and offer advice. Like if you, this might sound like heresy right now, but if you know Rust, the compiler of Rust has a lot of stuff built in to offer you advice on how to resolve problems and errors, and it notices when things might be wrong and offers quite nice hints on what to do. Doesn't always work, but it is one of the best things I've seen about the language, so something like that would be really sweet. And then, of course, you could have exploration of different kinds of composition strategies that I've already mentioned. So you might have different ways of doing that. And yeah, that's about it. Any questions? Here we go. Let's turn TTS back on so Minty can tell me to go suck my dick. God damn it. You guys are useless. How am I doing in time? I think I'm doing pretty well. I think that was like... Was that 30 minutes?
It was a very short and sweet, thank you.
Make the teapot spin faster, sure, why not? Wait, that didn't quite work out. There you go.
Yes, 30 minutes.
Okay, I can go a bit faster then. It was intentionally slowing myself down in specific places and repeating things, which might not be bad, but good. Then I'm good in time. Here you go, spinning too fast. Can't be fast enough, dude. You don't know shit. This is why you're not a programmer. Gotta go faster. There you go, overdrive. Also get this shit in here.
Why do Jews consider themselves an ethnicity if you can convert to Judaism?
Fuck do I know?
My question is, why doesn't the teapot have a cup friend?
Good question, sir. Should have one, I guess. Oh no. Gonna have to add more code for that though. Alrighty. Other things, let me read through chat.
Why did you choose a teapot for the demonstration? How much do I need to know about GLSL to use GLSL toolkit properly?
I chose a teapot because that's usually what people do. Teapot is kind of a staple joke thing in graphics. Lots of teapots. How much do you need to know about GLSL? Well, you know, because it takes in GLSL code, so I'm not sure how useful it will be for people that don't know GLSL at all. If you don't know, then it might be better to look into other kinds of projects like Vario, which is a sort of a compiler that takes Lisp source code and turns that into GLSL, which you can then use with GLSL toolkit to combine things. But GLSL isn't really a complicated language to learn. If you already know C, then you should know most of it. Really, pretty much C stuff aside from, you know, the standard library, which is different. So I don't know about using it properly though, because it's just, you know, unless you want to do semantic analysis, in which case you obviously need to know quite a bit about how things work. If you just want to merge things, then you need to just call this function and you're done. Yeah. Anything else? Bum, 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 bum. Yeah, I'll fix the color still. Pam-param. Pam-param. Pam-param.
What tea should I have today? Calming tea or thinking tea?
I don't know. How... What is thinking tea? Is that slang for drugs? Also, Minty, I'm so glad to see you again. I missed you.
Blackberry Sage's thinking.
Okay, sure. Go with that then, I guess. I don't know. I'm just some schmuck. Alright, if that's all, then I guess we're done, yeah. Do some video games, though.
It's the tea that makes you ascend to the astral realm.
Yeah. Hold on.
I missed you guys too, but I was overloaded with postal and then schoolwork.
You in question stands out too much. Well, complain to whoever made that font.